Hi everyone, and welcome to the second of 5 videos going through some past exam questions on buffer solutions. Right, this question is talking to us about butanoic acid, something about butter turning rancid, yeah, whatever. Right, what are we doing? Write the expression for the acid dissociation constant. Okay, right, so that is Ka. So it's going to be H plus, what we're doing, butanoic acid, so it's going to be this. Minus an H plus off the end. So let me COO minus. And then, yeah, just remember that you do need to use the square brackets to represent concentration. That does actually matter. Okay, so that's our Ka. It now wants us to calculate pKa. Anything, if it's acids, anything with a little p in front of it means we're doing the negative log. pH is the negative log of the H plus concentration. pKa is the negative log of the Ka. So if pKa is the negative log of the Ka, then it's going to be the negative log of 1.51 times 10 to the minus 5. That's why it's just a 1 mark question. The calculator will do this for us. We're going to do the log of 1.51 times 10 to the minus 5. So we've got minus 4.82, but we need to do negative log, so it's just going to be 4.82. Usually these are done to 2 decimal places. It doesn't say here, so they can't mark us down for decimal places here. Right, now we want to calculate the pH of the butanoic acid. So here we've got our Ka expression. If we want to know the pH, we're going to need to know the H plus concentration. Okay. Butanoic acid here, this is just a weak acid at this point. Okay, it's not a buffer solution. This question is going to go on and ask us about buffers later on. But at the moment, it's just asking us for the pH of butanoic acid. Butanoic acid is a weak acid. Okay, and the trick that we can use whenever we get weak acids is that when they dissociate, it produces one of each of these ions. So the concentrations of these two ions will be the same. So we can turn this into H plus squared. So we can say that Ka is going to be H plus squared divided by the concentration of butanoic acid. And then if we want the H plus concentration so that we can do the pH, we're going to multiply by this, and then we're going to square root it. And this should hopefully be a rearrangement that you get familiar with, because it happens quite a lot. So we can now go ahead and do this. So the H plus concentration is going to be the square root of the Ka, which is 1.51 times 10 to the minus 5. We just saw that. Times by the acid concentration, which it says is 0.25. So the H plus concentration is, let's work this out, 1.51 times 10 to the minus 5 times 0.25, and then the square root of that, 1.94 times 10 to the minus 3. So the pH is then going to be the negative log of that value. Do the log of that answer. And we get minus 2.71, but obviously we need to do the negative log, so it's just going to be 2.71. Yeah, it did say 2 decimal places. Okay. So that's where we should get to. The pH should be 2.71. Okay. So that should hopefully be a method that you get more and more comfortable with. If it's just a weak acid, convert the Ka into H plus squared. You get this rearrangement with the square root in it, put your numbers in, and then do the negative log at the end. Right, part B here is asking us to do what? We're adding butanoic acid to magnesium, then we're adding butanoic acid to sodium carbonate. Okay, write some ionic equations. All right, so if we've got butanoic acid, we're adding it to magnesium. It's going to make magnesium butanoate and hydrogen gas. But if we're doing the ionic equation, the butanoate ions from the acid are going to end up cancelling out. So we're going to end up with the H plus ions from the acid reacting with magnesium, and we're going to end up with magnesium ions and hydrogen gas, and then it just needs balancing like that. Okay, we'd have the butanoate ions here and the butanoate ions here, but they would cancel out. Okay. And then we want to see the ionic equation for butanoic acid and sodium carbonate. So again here the butanoate ions are going to cancel out. Okay, so we're going to have the H plus ions. The sodium cut here, we need to be really careful because carbonates are usually insoluble. Okay, so they're usually solids, and remember, if things aren't aqueous, then we can't cancel them out of the equation. But here it does specifically say aqueous sodium carbonate. So what would happen here is we're going to end up making, if we think about this reaction, it's going to make sodium butanoate, right, and water and carbon dioxide. Well, we already know the butanoate ions are going to cancel, but the sodium ions are going to cancel out as well. So we're just going to have hydrogen ions and the carbonate ions reacting together to make the water and the carbon dioxide. Okay, the sodium ions from the carbonate and the sodium butanoate would cancel, and the butanoate ions would cancel. And then again, we just need to balance this. We need to have two hydrogens here. Okay. Right, carrying on with this question, this is now the bit where it starts talking about buffer solutions. So we're adding butanoic acid to some sodium hydroxide, and it makes a buffer solution, and we've got to explain why. And we saw this question in the previous video. So why does a buffer solution form? To get a buffer solution, you need to have a solution that contains both a weak acid and its conjugate base. Okay. So the key thing with this is that if these two react together, it's going to make the conjugate base. So when butanoic acid reacts with sodium hydroxide, it forms sodium butanoate. So that's part of our buffer solution because that's the conjugate base. But we also need the weak acid. And so the key thing here is that it's a partial neutralization. Can you see that we've used the same volume of both of them, but the concentration of the butanoic acid was much higher than the sodium hydroxide. So we had an excess of butanoic acid. So when these two react, there's still going to be some butanoic acid left over. So we can say after the reaction, some butanoic acid remains in solution. Because an excess was used. And so this is the key thing, that we've now made a solution that has butanoic acid and sodium butanoate in it. Okay. It's always good practice to name the chemicals or write the formulas rather than just say the weak acid and its conjugate base. So yeah, I've done the names, you could do the formulas, that'll be fine. Right, here's now the calculation then when we've got to calculate the pH of the buffer solution. And this is a 5-mark question, so it's going to be a fair bit of work here in terms of calculating this. We're going to start, as always, with Ka. Ka is your friend. It shows you what you've got to do. What are we doing? We're doing butanoic acid still. So actually we could just, we wrote the Ka of this out earlier on, didn't we, in this part of the question. So I'm just going to copy it from here. Okay, so I'm just going to write this out again just so I can see it in this part of the question. So I'm just copying that from earlier on. And this time, because it's a buffer solution, we're not going to be allowed to do this turning into H plus squared, okay, because these two concentrations are no longer going to be equal to each other, because we're going to be getting the butanoate ions from the reaction that we talked about, as well as just getting it from the acid dissociating. So these two are not going to be equal to each other anymore. Okay. But we do still need to rearrange this. we need the H+ concentration if we're going to calculate the pH, so we do need to switch this around. But we're not going to do any other fiddling with it, it's just swap it around. So it's going to be Ka multiplied by this acid concentration divided by the other one. Okay, and then the way that we've made this buffer solution up, we made it by reacting the sodium hydroxide with the butanoic acid. So we need to write that equation out, and then we need to use the same table method that I showed you in the previous video. So we're going to want our butanoic acid plus our sodium hydroxide. It's going to make, again, I'm going to write the sodium butanoate separately. We'll write it as sodium ions and butanoate ions because we're only interested in the ion. And it's going to make water. And we're going to do this in a table. We're going to do this ice table that we mentioned before. Try and actually leave myself enough room to finish the calculation this time. Got a bit squidged in the previous video. Right, let's put this in here. We're not going to bother about the water. It's not going to be relevant to our Ka expression. We're not going to bother with the sodium ions. That's not relevant either. We're interested in the butanoate ions, and we're interested in the butanoic acid. And we are also interested in the sodium hydroxide because we need that to get us started. So we need to work out the initial numbers of moles. Okay, and do we? Yes, we do. So we're going to use these values from the top of the question here. So the butanoic acid, we're going to do the N equals C times V to get the number of moles. So for the butanoic acid, it's 50 centimeters cubed, so it's 50 over 1,000 to get it into decimeters cubed, and times it by 0.25. And then for the sodium hydroxide, we're going to do the same thing, but with these values. So it'll be 50 over 1,000. And we're going to times it by 0.05. So this is what we're doing here. 50 over 1,000, and we times it by 0.25 is 0.0125. That is the moles. There's no way I'm going to have space for this. Okay. So that goes in here. And then this one is going to be the moles of the sodium hydroxide. 50 divided by 1,000 times 0.05. 2.5 times 10 to the minus 3. So that is here. And we wouldn't have had any butanoate ions to start off with because we just mixed these two together. So this is good. It shows us what we mentioned up here. We said that we had an excess of the butanoic acid, and we can see that in the numbers that we've calculated. So that's good. So what that means is that all of the sodium hydroxide is going to get used up. Okay. So we're going to use up all of that, and we're going to end up with nothing. So we're not going to bother using that value. These react in a 1-to-1 ratio. So we're going to use up the same amount here. Okay. So if we then do, I'm pretty sure I can do that in my head, but I'm just going to check it. 0.0125 take away 2.5 times 10 to the minus 3. Yeah, is 0.01. And we're going to add that value here because this is the product. So we're going to end up with 2.5 times 10 to the minus 3 moles. Right, we can't put these values in because we need to convert them into concentrations. Okay, that's why we have the square brackets here. These are moles. So we're going to need to divide by the volume. So the volume is going to be the total volume from up here. So we had 50 centimeters cubed and another 50 centimeters cubed. So it's 100 centimeters cubed, which is 0.1 decimeters cubed. So we're going to just put this in a different color here so you can see. So we're dividing by 0.1, and we're going to divide this by 0.1. To end up with our concentrations. So we're going to end up with a concentration of 0.1 moles per decimeter cubed, and we're going to end up with a concentration of 0.025. These values are now ready to substitute in to our Ka expression here. So I'm going to try and squeeze this in the gap here. So our H plus concentration is going to be Ka, which is 1.51 times 10 to the minus 5, times by the acid concentration, which is 0.1, divided by the 0.025. So let's calculate that. Times 10 to the minus 5 times 0.1 divided by 0.025. 6.04 times 10 to the minus 5. And then we're going to use this to calculate the pH. So the pH is going to be the negative log of this value. So we're just going to do the log of that answer and put a minus in front of it. So it's 4.21, so it's going to be 4.22. Did it say 2 decimal places? Yeah, it did. pH is always done to 2, well, always. 99% of the time, pH is done to 2 decimal places. So it's usually, you don't usually get caught out with decimal places because you kind of just get in the habit of doing it to that number of decimal places. Okay. So hopefully you can see that that is the same method that I showed you in part 1 of these videos. Okay, so hopefully you can practice this and get used to using this table. But there is a final bit of this question. Let's just have a look at this one here. So they're adding methanoic acid now to butanoic acid. And we end up with these acid-base pairs. So complete the equilibrium below and work out what's going to happen. Okay, so these are both weak acids. So how are we going to know which one is going to be the acid and which one's going to be the base? This is going to be look at the Ka values. So we know this was our Ka value from our butanoic acid, 1.51 times 10 to the minus 5. The Ka for our methanoic acid is 1.82 times 10 to the minus 4. So this has got a bigger Ka value, because it's 10 to the minus 4 instead of 10 to the minus 5. Remember, if it's got a bigger Ka value, if you look at what Ka is showing you, not that one, this one, if Ka is bigger, it's going to mean the H plus concentration is bigger. And so it's going to be a stronger acid. So the methanoic acid here is going to be the stronger acid of the two. It's going to give a proton to the butanoic acid. So we're going to end up with the methanoic acid as a negative ion, and the butanoic acid is going to be acting as the base and accepting a proton here. It's going to end up as H2 plus. So then we say this is acting as the acid, we'll call that acid 1. This is going to be acting as the base, so this would be base 2. And so this is a conjugate acid-base pair, methanoic acid and methanoate ions, so this would be base 1, and this therefore is acid number 2.